So, good evening, everyone. Today is week 9 of our NPTEL course Introduction to Algebraic Geometry and Commutative Algebra. So, this is a course taught by Dr. Dilip Patil. Today is our week 9, and we will do some problems from uh, the topic Finite Algebras over a Field and Hilbert's Null Stellenjas. Uh, so, yeah, uh, let us start with the first problem that says that for each part, uh, uh, yeah, so for each part we give a short and rigorous proof in a question answer format, and let's start the first question. Uh, we have to show that each of the following sets is not an algebraic set. Uh, the first one is given by this, that the set of all tuples from A to R, that is affine space over R, such that y equals to sin x. We have to show that it is not an algebraic set. Now the first answer is like this, that suppose toward a contradiction, uh, uh, we say that the graph of sin x is algebraic in A to R. This implies that we have to show that it is a zero set of a polynomial or some polynomials. Now then there exists a non-zero polynomial p x comma y which equals to ai of x comma yi of yi. That means we are writing it in as a polynomial over y, where coefficients are depending on x. AIX are coming from this Rx, such that p of x comma sin x is 0 for all x belongs to R. Now fix n plus 1 distinct real numbers t0, t1 up to tn in the open interval -1 to 1. Now for each j, the question sin x equals to tj has infinitely many real solutions, because sin is periodic. Therefore you will get the same value for infinitely many x. Let x suffix j comma k, where k is running over z, be such a sequence with sin x jk equals to tj for all k. Evaluating p as these points gives sum of ai of x j comma k of t to the power I j equals to 0, where I is running from 0 to n for all k belongs to z. For fixed j, the left hand side is a polynomial in x, and it has infinitely many zeros, x suffix j comma k. Hence it is the zero polynomial in x. Thus for each j, the identity summation ai of x dot t to the power I suffix j equals to 0. Now see that for each j, this identity holds as a polynomial in x. Now viewing this as a linear system in the unknown polynomials a0x comma up to anx with coefficient matrix, the van der Waals matrix t to the power I suffix j, where I and j running from 0 to n, and using that the tj are distinct, so the van der Waals determinant is non-zero, and we conclude that ai of x is 0. Hence p equals to 0, contradicting the choice of p as a non-zero polynomial. Therefore the graph of sin x is not an algebraic set. Next, let us focus on this A similar problem to what we did in the first, that we have to show that the set of all xy of a to r, where y equals to cos x, is not an algebraic set. Okay, let us try this for 5 minutes, then we can start discussing this. Okay, so let us start solving this. Yeah, So as of now you can understand that the argument is identical to part 1. If a non-zero polynomial p which equals to summation aix y to the power I vanished on the set x comma cos x, choose n plus 1 distinct values t0 to tn from -1 to 1. Now for each tj, the equation cos x equals to tj has infinitely many solutions. Evaluating p at those infinitely many x's shows that the polynomial combination summation aix to the power ij is identically 0, and the resulting van der Monde linear system forces all ai equals to 0, so p equals to 0 and contradiction, hence the graph of x is not algebraic. Now let us try again this third problem that says that set of all x comma y from a to r such that y equals to e to the power x. Okay, so let us focus on the problem 3. So again we have to show that it is an algebraic set, we have to show that it is a zero set of a polynomial. So assume that there exists a non-zero polynomial pxy with px comma ax equals to 0. Now we write the relation as anx e to the power nx plus an minus 1x e to the power n minus 1x plus up to a0x equals to 0 for all x belongs to R. Now divide both sides by e to the power nx to obtain anax plus a to the power n minus x an minus x e to the power minus x plus up to a0x e to the power minus x equals to 0. Now let x tends to infinity. The terms e to the power minus kx tend to 0 for all k greater than equals to 1. So the left hand side tends to anx when x is large, and in the sense that exponentially small terms cannot cancel a non-zero polynomial anx for all sufficiently large x. More directly, because the equality holds for all real x fixed any sequence xm going to infinity, the terms an minus 1 xm e to the power minus xm to a0 xm e to the power minus xm tend to 0. Hence an xm goes to 0. But an is a polynomial, so the only way an xm goes to 0 for unbounded xm is that an is the zero polynomial. Thus an equals to 0, contradicting the assumption that p has degree n in y. Repeating the argument inductively yields a contradiction unless all ai equals to 0. Therefore no non-zero p exists and the graph of ex is not algebraic. Next, again let us focus on this problem that set of all z comma w from a to c such that z square plus w square equals to 1. Yeah, okay, let us focus on this. Okay, so let us start understanding this. Uh, yeah, so an algebraic subset of A to C is the common zero locus of the polynomials in the holomorphic variables Z, W, and now the condition that mod Z square plus mod W square equals to 1 can be rewritten as Z dot Z bar plus W dot W bar equals to 1, which involves the conjugates Z bar comma W bar and is therefore not a complex algebraic equation. To make this into a precise contradiction argument, suppose there exists a non-zero polynomial pz comma w equals to summation ij equals to 0, which is running over n comma n cij z to the power I w to the power j from c z comma w, such that pzw equals to 0 for every z comma w with z square plus w square equals to 1. Now fix any w0 with mod of w0 less than 1. Then the circle z comma c with mod z equals to root over 1 minus w0 square is an infinite set, and for every z on that circle the pair z comma w0 lies on the given set. Hence pz comma w0 equals to 0 for all such z. For fixed w0, this is a polynomial in z which vanishes on an infinite set with an accumulation point. So it must be the zero polynomial in z. Thus all coefficients of power of z in p z comma w0 vanish, and so for every exponent I the polynomial qi(w) equals to summation of cij w to the power j satisfies qi(w0) equals to 0. Since this holds for every w0 in open disk w such that mod of w less than 1, each qi vanishes on an open set and hence is the zero polynomial. Thus Cij equals to 0 for all I comma j. Therefore P equals to 0, which is a contradiction. Consequently the sphere mod z square plus mod w square equals to 1 is not a complex algebraic set. Now next let us focus on this set, that is the tuples from A3R such that it depends on single variable t which is from R, such that cos t comma sin t comma t belongs to A3R. We have to show that it is not a zero set of some polynomials. Okay, so let us try to solve this. Suppose there is a non-zero polynomial p. You know that this polynomial will be in three variables. So let us the polynomial variables are x comma y comma t, and suppose there is a non-zero polynomial px comma y comma t vanishing on the set cos t sin t and t, and write px comma y comma t as summation of pkx comma y t to the power k, where k is running from 0 to d and pkx comma y belongs to rx comma y. Now fix t0 of r. For every integer m we have p of cos t0 plus 2 pi m comma sin t0 plus 2 pi m comma t0 plus 2 pi m equals to 0. But cos t0 plus 2 pi m equals to cos t0 and sin t0 plus 2 pi m equals to sin t0. So summation of pk cos t0 comma sin t0 of t0 plus 2 pi m to the power k equals to 0 for all m belongs to z. Now for fixed cos t0 comma sin t0, the left hand side is a univariable polynomial in the integer variable m, which takes the value 0 for infinitely many integer n. Hence it must be the zero polynomial in M, and equivalently for each k we have pk of cos t0 comma sin t0 equals to 0. Since t0 was arbitrary, every coefficient polynomial pk of x comma y vanishes on the whole unit circle x square plus y square equals to 1. But a polynomial in R of x comma y that vanishes on the unit circle must be divisible by x square plus y square minus 1. Therefore, we may write pk of x comma y equals to x square plus y square minus 1 into qk of x comma y for some qk r of x comma y for each k, and hence p of x comma y comma t equals to x square plus y square minus 1 into qx comma y comma t for some q coming from x comma y comma t. But on the set cos t comma sin t comma t we have x square plus y square minus 1 equals to 0. So the factorization shows nothing new. To reach a contradiction, we iterate the previous argument, restricting p to the circle forced each pk to vanish on the circle. Hence each pk is a multiple of x square plus y square minus 1, and substituting back and factoring out x square plus y square minus 1, if p were non-zero, there must remain a factor not divisible by x square plus y square minus 1. But repeating the same integer shift argument with that factor leads to the conclusion that all coefficients vanish. And concretely, since t0 was arbitrary, we deduce pk vanishes on the circle for all k. So p of x comma y comma t vanishes identically on the Zariski dense set x comma y comma t such that x square plus y square minus 1 equals to 0 only if p is divisible by x square plus y square minus 1. If p not equals to 0, dividing by x square plus y square minus 1 repeatedly is impossible indefinitely in the polynomial ring. So the only resolution is p equals to 0, which is a contradiction. Thus the given curve is not algebraic in A3R. Now let us focus on the next problem, which says that union of Lm, where Lm is the line v of y comma y minus mx, that is the zeros of x comma y such that which satisfies y minus mx in A2R. So we have to show that this is not an algebraic set. So by this we will show that the finite union of the infinite union of algebraic sets is not algebraic set, which gives us the natural definition of an algebraic set or the Zariski topology. Let us try this for 5 minutes and we will try. Okay, so let us solve this. The set in question is the countable union of distinct affine lines S equals to union of Lm, where Lm is your set x comma y of R2 such that y equals to mx. Now recall that the Zariski topology on A2 is Noetherian. What does this mean? That every descending chain of algebraic sets stabilizes. That means, and in particular, every algebraic set decomposes as a finite union of irreducible components. Each line Lm is an irreducible algebraic subset. Now, if S were algebraic, it would have a decomposition into finitely many irreducible components. Hence, it could contain only finitely many distinct lines. But S contains infinitely many distinct lines Lm, a contradiction, and equivalently the ideal of S is Is equals to intersection y minus mx, where m is running over z, an infinite intersection of distinct prime ideals. In a Noetherian ring, every radical ideal is a finite intersection of prime ideals, so Is cannot be radical of a finitely generated ideal unless only finitely many primes occur, and hence S is not algebraic. Now let us focus on to the next problem, which says that show that each of the following sets in an algebraic set is an algebraic set, and find generators for the ideals of algebraic sets in A, C and D, and also you work over a field K unless otherwise indicated. When the statement names a specific ground field, that means it can be real or complex, we interpret coordinates and polynomials over that field. Now let us look at the first problem. We said that finite subsets of A in K. We have to show that it is an algebraic set. So the claim says that any finite subset S, suppose the elements are P1 up to Pr, is algebraic, and its vanishing ideal is I, which is intersection of all the maximal ideals, which looks like this. Yeah. The maximal ideal of the point P1, P suffix 1 prefix j up to P suffix n prefix j. So these are tuples for the P prefix j, and we have to show that this ideal, which is intersection of the all maximal ideals, is responsible for this finite subset to be algebraic. Now you can try this for 2-3 minutes, then you can start. Okay, so let us start solving this. Now, for a single point P of nk, the ideal MP consists exactly of the polynomials vanishing at P, right? That means it is clear that the V of MP, which is a single point P, is algebraic. Now, uh, a finite union of algebraic sets is algebraic, because if x equals to vi and y equals to vj, we would have that x union y is v of ij. So s equals to second bracket p1 up to second bracket pr, which is the second bracket p1 comma up to pr, which is union of v of all those maximal ideals, which is v of product of those maximal ideals, showing that S is algebraic. Now the vanishing ideal Is equals intersection of I of Pj, where j is running from 1 to r, which is equals to intersection of Mpj, which is the standard description of the vanishing set of a polynomial. Now so therefore we have shown that this any finite set of affine space is an algebraic set. Now next let us show that this set of polynomials is a now this set, that cos t comma sin t of a to r, where t is running over as r, is an algebraic set. Okay, so the set cos t comma sin t, where t is running over r, is the real affine algebraic set defined by x square plus I square minus 1 equals to 0. That means it equals to which equals to v of x square plus y square minus 1. Now for every real t, we have cos square t plus sin square t minus 1 equals to 0. So the parameterized set is contained in v of x square plus y square minus 1. Conversely, any real point x comma y with x square plus y square equals to 1 is of the form cos t comma sin t for some real t. Hence, the two sets coincide. Thus, the circle is an affine algebraic set cut out by single polynomial x square plus y square minus 1. Now, over R, the polynomial x square plus y square minus 1 is irreducible. So, the ideal of the circle is the principal prime ideal x square plus y square minus 1. Now, we go to our next problem, which is we have to show that the twisted cubic, that is t comma t square comma t cube, is an algebraic set. But this is fairly easy to see, because by the claim you can see that the zero set should be the y component t square minus x square, which is the t. So t square minus t square would be 0. So definitely the y minus x square should be there. And also, if you take the y component t square to the 3 times and t cube 2 times, you would again see that it should be y cube minus z square. Again, if you take x and z component, then you can see that z minus x cube. So any two of them is fine. Now to prove this formally, consider the K algebra homomorphism phi of kx comma y comma z to kt, where x is going to t, y is going to t square, and z is going to t cube. And you can see that the image phi is the K sub algebra. Besides the ideal of polynomials vanishing on the set C, and clearly y minus x square and z minus x cube lie in the kernel phi Hence y minus x square and z minus x cube belongs to kernel of phi. Conversely, quotienting by these two relation gives k of x comma y comma z by y minus x square comma z minus x cube belongs to isomorphic to kx via the map induced by x going to x and replace y by x square and z by x cube. Now since kx is an integral domain and the composition with phi is the canonical surjection k of x comma y comma z to kt identifying x with t, we deduce that kernel of phi is y minus x square comma z minus x cube. Therefore, the zero set of C is y minus x square comma z minus x cube and C equals to v of y minus x square comma z minus x cube uh, is algebraic and therefore it is therefore our proof is done. Now let us focus on the next problem and t to the power to the power m comma t to the power n all the tuples from a to c where t belongs to c, where m and n are relatively prime integers, and you can see that for m comma n for GCD of m comma n equals to 1, the monomial curve Cm comma n equals to t to the power n comma t to the power n t belongs to c which is contained in a to c is algebraic and its defining ideal is principal, which is I of c of m comma n, which is y to the power m minus x to the power n belongs to c of xy. So we have to show that this is an algebraic set. You can try this for 2-3 minutes, then you can start. Okay, so let us try to solve this. Define the map Cx psi from Cxy to Ct from x going to t to the power m and y going to t to the power n. Then every polynomial in the image evaluated at t takes the form f of t to the power m comma t to the power n. The polynomial f x comma y equals to y to the power m minus x to the power n satisfies f of t to the power n comma t to the power n equals to f t to the power nm minus t to the power nm equals to 0. So y to the power m minus x to the power n belongs to car of psi. Thus c comma mn belongs to v of y to the power m minus x to the power n. To prove equality of sets and of ideals, let a comma b belongs to v of y to the power m minus x to the power n. So b to the power m equals to a to the power n. We must show there is some t of c with a equals to t to the power m and b equals to t to the power n. Since c is algebraically closed and GCD of m comma n is 1, there exist integers u comma v with um plus bn equals to 1 and set t equals to a to the power u and b to the power v. Now compute t to the power t to the power m equals to a to the power u and b to the power v of m equals to a to the power um dot b to the power vn equals to a to the power 1 minus vn of b to the power vm equals to this and which equals to a, because b to the power m equals to a to the power n. And similarly you can get that t to the power n equals to b, and hence a comma b which equals to t to the power m comma t to the power n lies in the parametrized image. Therefore v of y to the power m minus x to the power n equals the image c of m comma n, so the variety is algebraic. Now finally we show curve of psi equals to y to the power m minus x to the power n. Now consider the induced map psi bar from cx comma y mod y to the power ideal generated by y to the power m minus x to the power n to c of t to the power m comma t to the power n, which is contained in Ct, and this map is surjective by construction and the domain has Carl dimension 1, and hence psi bar is an isomorphism onto its image. Thus car psi, which equals to ideal generated by y to the power m minus x to the power n, we conclude that the vanishing ideal is generated by the single polynomial y to the power m minus x to the power n. Therefore we have completed our proof. Now next there is a problem 9.9 which says that let k be an arbitrary field and let s equals to the set of all polynomials from k x1 comma xn such that vkf equals to phi be the set of polynomials having no zeros in k to the power n, and let a is an ideal k x1 to xn be an ideal, and prove if s intersection a is phi then vka is not equals to phi. So let us prove this. We prove the equivalent contrapositive statement that says that if vk is phi then a intersection a is not equals to phi. Now assume that vk is phi. By definition this means that for every point q of k to the power n there exists some polynomial fp of a with vk fpp not equals to 0, and for any polynomial f of k x1 to xn denoted by d of f as x of k to the power n such that fx not equals to 0 by the basic Zariski open set determined by f. The preceding observation says that the family df f belongs to a is an open cover of k to the power n such that k to the power n equals to union of df where f is coming from a. Now invoke the Noetherian property to affine space with the Zariski topology. The topological space k to the power n is Noetherian, hence every open cover admits a finite subcover. Therefore there exist finitely many polynomials f1 to fr such that k to the power n equals to d of f1 union up to d of fr. Now consider the product f equals to f1 dot dot up to fr which belongs to A, which lies in A because A is an ideal. Now for any point x of k to the power n, some dfi contains x, hence fi x not equals to 0, and therefore f of x not equals to 0. Thus f has no zeros in k and equivalently f belongs to S. And we have found f belongs to A intersection S, so A intersection S is not phi. This proves the contrapositive, hence the original statement. So this completes our all the assignments done today, and therefore we complete our class today. Thank you.